Welcome to my Organic Chemistry 2 multiple choice practice tests. So let's jump right into it. Number one, what is the major product in the following reaction? So what do you think the answer is to this problem? So notice that we have an aldehyde functional group and we have silver oxide. Whenever you have the Ag plus ion, it could be in the form of silver oxide, or it can be written like this. It can be complex to ammonia. These reagents is associated with the Tollens reagent, and it can oxidize an aldehyde to a carboxylic acid. It's very specific for aldehyde functional groups, and even alpha hydroxy ketones as well. But for the most part, they react with aldehydes. So A is not an aldehyde. It's out. C is a ketone, so it won't work. If we had an OH here, where an alcohol on the alpha carbon, then it would work. That's the alpha hydroxy ketone. But since it's not there, C is not the correct answer. So now we're between B and D. B is the protonated form of the carboxylic acid. D is the deprotonated form of it. So to distinguish between B and D, you need to look at step 2, which is H3O+. Under acidic conditions, the carboxylic acid will be in its protonated form, so the hydrogen should be here. So the answer is B. Number 2, complete the reaction. By the way, for these questions, feel free to try the problem yourself, pause the video, and then unpause it when you're ready to see what the answer is. So let's begin. We have 1-ethyl-4-isopropyl benzene, and we're going to mix it with bromine in the presence of ultraviolet light. So this is going to be a radical bromination reaction. Now we can eliminate answer choice B and D because this reagent will not put a bromine atom on the benzene ring. The only way to do that is to use Br2 in the presence of a Lewis acid catalyst like FeBr3. So since we don't have that, answer choice B and D is out. So what this reaction will do, radical bromination, it's going to replace the benzylic hydrogen, which could be the hydrogens in purple or in green. Now we have both answers. Answer choice A, we replace the purple hydrogen, and for answer choice C, we replace the green hydrogen. So the question is, which one is better? What type of carbon do we have here? Notice that that carbon is connected to 3 other carbon atoms, the 2 methyls and this carbon, so it's tertiary. And this carbon here is a secondary carbon because it's attached to 2 other carbon atoms. So which radical is more stable, a secondary radical or a tertiary radical? Because tertiary radicals are more stable, the bromine will selectively abstract the tertiary hydrogen to create a tertiary radical. So therefore, answer choice C is the correct answer. Let's review some reactions associated with bromine. So let's say if you have an alkane and you use Br2 with HV. By the way, this is the same, it has the same effect as using NBS. It's a radical bromination reaction. Now what's going to happen is bromine will selectively replace the tertiary hydrogen. So it's just going to add a Br to the tertiary carbon. Now let's say if we use NBS on pentane. So here we have a primary hydrogen, and here we have a secondary hydrogen. This is another radical bromination reaction. It's going to replace the highest substituted hydrogen, in this case the secondary one, rather than the primary one. So we're going to get this as an answer. Now it can also replace this one as well because both of these are secondary and they lead to different products. So the bromine atom is going to go on the most substituted carbon. For this example, the most substituted carbon is the tertiary one, and for this one, it's the secondary carbon. So that's what happens if you add Br2 with HV, or NBS to an alkane. Now let's say if you add it to an alkene, the bromine under radical conditions will not react with the double bond. What's going to happen is it's going to replace the allylic hydrogen, the one that's one carbon away from the double bond. So you're going to get this as an answer. And if you have a benzene ring, it's going to replace the benzylic hydrogen. So basically, the bromine atom is going to go one carbon away from the benzene ring, which is kind of the same as this situation where it's one carbon away from a double bond. So the bromine atom is going to replace the hydrogen on the benzylic carbon, which is one away from the benzene ring. Now, let's say if you have an alkene, and let's say if you add Br2 in the presence of dichloromethane. This is not a radical reaction. In this situation, the bromine reacts with the double bond, and the double bond is going to disappear. So it's going to add two bromine atoms anti-addition. Now you also get the enantiomer, which looks like this. So you get a mixture of two products. Now if you have a benzene ring, Br2 by itself will not react with the benzene ring. If you want to add the Br directly to the benzene ring, you need to add a catalyst like FeBr3. So what's going to happen is it's going to replace the hydrogen with a bromine atom. And so you get this as a product. Now let's say if you have an alkene, if you add HBr, it's going to react with the double bond, and it's going to put a bromine on the more substituted carbon, which is the secondary carbon. And the hydrogen will go on the less substituted carbon. Now let's say if you add HBr and peroxides, it can be written as H2O2 or ROOR. In either case, there's two oxygen atoms that are single bonded to each other, and that's a peroxide. So what's going to happen is the bromine is actually going to go on the less substituted carbon. So we get the anti-Markovnikov reaction rather than the Markovnikov reaction with just regular HBr. So just make sure you're familiar with those reactions. So you might see bromine in those different forms, and just keep that in mind for your next organic chemistry final exam. Number 3, which compound has a proton with the lowest pKa? So let's compare different compounds. Let's start with the alpha hydrogen for the compound in answer choice C and in answer choice B. Which of those two hydrogens is more acidic? Well, whenever you have an alpha hydrogen between two carbonyl groups, the pKa is around 9. For a hydrogen next to one ketone, it's roughly around, I believe, 20. Now, this hydrogen here, between the ketone and the ester, is 11. The reason for that is because of this electron donating group. Because the OET group, the oxygen, can donate a pair of electrons to one of the carbonyl groups, it makes this hydrogen slightly less acidic, so the pKa goes up a little. Anytime you add an electron donating group to an acid, the pKa goes up. It becomes less acidic. If you add an electron withdrawing group to an acid, the pKa will go down. It becomes more acidic. Now, the most acidic hydrogen for the carboxylic acid is this one here. The pKa for a typical carboxylic acid is around 4 to 5. So the carboxylic acid is much more acidic than compound B or compound C. So we can eliminate B and C. Now the reason for this is, if you notice the trend on the periodic table, let's say this is carbon, nitrogen, oxygen, fluorine, chlorine, bromine, and so forth. Acid strength increases as you go to the right and as you go down. So when comparing a CH bond versus an OH bond, usually 99% of the time the OH bond is more acidic. So here, this is a carbon-hydrogen bond. The pK is 11. Here, this is an oxygen-hydrogen bond. It's much more acidic, 4 to 5. But keep in mind, these are general trends, though. So you might see an exception or two. Now, this is a protonated carboxylic acid. So this is even more acidic. The pKa of a protonated carboxylic acid is somewhere in the negatives. It could be like -4, -5, but it's much less than positive 4 to 5. So the correct answer is D. Whenever you see a hydrogen that's attached to an atom with a positive charge, it's very acidic. For example, the difference between H2O and H3O+. H2O has a pKa of 15.7, it's neutral. But H3O+, the pKa is around like -3 or -4. As you can see, that extra hydrogen makes it a lot more acidic. Number 4. Which structure is most consistent with the following IR spectrum? Now, the first thing you want to look at is this huge bulky peak around 25 to 3300. You can't miss it. When you see a massive, very strong, very broad signal in this region, you have a carboxylic acid. This is the OH stretch of a carboxylic acid. So we can eliminate answer choice C and answer choice D because they're not carboxylic acids. The next important signal that we have here is the carbonyl group at 1700. That's also part of the carboxylic acid functional group. Now the ketone would also have that signal at 1700, but the ketone wouldn't have this very broad signal. Now granted, we do have an alcohol, and an alcohol would generate a broad signal, but it wouldn't be around 25 to 3300. This signal would be more like 33 to 3500. And it's not as broad as a carboxylic acid. So if I can draw a rough sketch, an alcohol OH stretch would look something like this. It would be in that region. It wouldn't cross over past 3000. It wouldn't go to the right of 3000. So we can eliminate D. Another reason why we can eliminate answer choice D is this signal here. That signal, which is roughly around 1200, it's a CO stretch, but not for an alcohol, but for a carboxylic acid. There's two types of CO stretches. There's the CO stretch of an alcohol and an ether, where this is an sp3 carbon. That's around usually 1000 to 1150, so we'll say like 1100. And then there's a CO stretch that's next, where the carbon is sp2 hybridized, and that's this carbon. The carbon from a carboxylic acid, that's sp2 hybridized. So that CO bond is a little bit more than 1100. It's like 1200 to 1300. So this signal, which is roughly around 1200, that correlates to a CO stretch where it's an sp2 hybridized carbon rather than an sp3 hybridized carbon. So that's another reason why it's not the alcohol. Now there's another signal that we can look at, and that is the C triple bond C at 2200. This will distinguish the right answer from the rest. So only answer choice B has a carboxylic acid with an alkyne. So that signal at 2200, it could be a C triple bond C, or even a nitrile, a C triple bond N, but we don't have a nitrile. So we can eliminate A because we don't have an alkyne, we have an alkene. And an alkene, we should see a signal somewhere between around 1600 for a C double bond C. So the correct answer for this problem is answer choice B. We have the OH stretch of a carboxylic acid, the carbonyl stretch, and the alkyne, and also the CO stretch for a carboxylic acid. But to the right of 1500 is the fingerprint region, so this region is not always reliable. So you can use that as a last resort. Number 5. Which set of reagents will produce p-Nitrobenzoic acid from benzene with the greatest yield? So go ahead and take a minute and see if you can get the right answer. So I'm going to go through every choice, but first let me show you how you can quickly get the right answer. The first thing you want to keep in mind is that we need para. We need the NO2 and the carboxylic acid group to be para with respect to each other. So we know we can eliminate answer choice B, because once you put the NO2 on the ring, it's going to tell the methyl group to go in the meta position, which we don't want. So B is out. Now, looking at answer choice C, we can eliminate that as well. Once we add the methyl group, it's an orthopair director, but notice that in step 2, when you oxidize it with potassium permanganate, it's going to convert it to a carboxylic acid, which is a meta director, and that's going to tell the NO2 group to go in the meta position. So C is out. Now, the only issue with D is once you add the NO2 group in the first step, and once you reduce it with tin and hydrochloric acid, it turns into an NH2 group. Now, granted, an NH2 group is an orthopair director. However, once you add a Lewis acid catalyst, you're going to deactivate the NH2 group, and it becomes a meta director. And so, step 3 won't even work in the presence of an NH2 group. The Friedel-Crafts alkylation doesn't work well in the presence of an amine. But A is the best answer. So let's go through each one. I'm going to go over A last, but let's start with answer choice B. So starting with benzene, so once we add nitric acid and sulfuric acid, we're going to replace a hydrogen with an NO2 group. So this is called nitration. And then we're going to add methyl chloride with an aluminum chloride acid catalyst. Now, the nitro group is a meta director, so it's going to tell the methyl group to go here. So we're going to put the CH3 on this side. And then once you add potassium permanganate with H3O+, it's going to oxidize this group. And it's going to convert it to a carboxylic acid. So we end up getting meta nitrobenzoic acid rather than para. So that's why we can eliminate answer choice B. So now let's see what we get for answer choice C. So starting with benzene, we're going to add methyl chloride first. As soon as we add the methyl group, what we now have is called toluene. That's the benzene ring combined with the CH3. And then once we oxidize it with potassium permanganate in H3O+, it's going to convert into a carboxylic acid. And then once we add nitric acid and sulfuric acid, the carboxylic acid is going to direct the NO2 group to go to the meta position. So we actually get the same answer. That is meta-nitrobenzoic acid. So now let's consider answer choice D. So step 1 is nitration. And then following step 1, we have reduction. So you can use any active metal. So you can use tin with hydrochloric acid. You can use zinc metal with hydrochloric acid. You can even use iron metal with hydrochloric acid. And what's going to happen is it's going to convert the nitro group to an amine group. So when you have an NH2 and a benzene ring, the name is called aniline. So now, if we add methyl chloride with the aluminum chloride catalyst, notice what happens. Aniline has a lone pair. It's actually quite nucleophilic. So what's going to happen is it's going to combine with the Lewis acid catalyst. So the methyl won't even go on the ring. So now the nitrogen is bonded to the aluminum chloride, and it also has two hydrogen atoms. So when nitrogen has 4 bonds, it now has a plus charge. When you have a nitrogen with a lone pair, it is an ortho-para activator. But now when it has a plus charge, it is a meta-directed deactivator. So if we mix a 1-to-1 ratio with aniline and methyl chloride with this catalyst, the ring is deactivated and the catalyst binds to the nitrogen, so it won't help the ring to react with the methyl chloride, so the reaction stops here. So there's no point in adding potassium permanganate because there's no methyl groups to oxidize. So just keep in mind that the Friedel-Crafts alkylation reaction and the acylation reaction does not work in the presence of an NH2 group on a benzene ring. So now let's look at our correct answer, which is answer choice A. So the first step is Friedel-Crafts alkylation. The catalyst, aluminum chloride, helps remove the chlorine from the methyl group, and so that gives us toluene. Now in the next step, we have nitration. Once you add toluene, the ring is slightly activated. Alkyl groups are weakly activating groups, so the ring is a little bit more reactive than before. So once we add the NO2 group, the methyl group will direct it ortho or para. Now we're going to write the para answer because that's the one that's going to lead us to our product. And then once we add potassium permanganate, the methyl group will be oxidized to a carboxylic acid. And that's the answer that we want. So thus we have para nitrobenzoic acid. By the way, if you want more practice problems, click a link that is in the description section of this video, and you can get access to more practice problems to prepare for your exam. The video that you're currently watching only has 15 free practice problems, but the paid version includes those 15 practice problems in addition to another set of 85 questions for a total of 100 practice problems. So if you think you might need more questions to work on to prepare for your exam, you can check out that video and let me know if you have any questions. Number 6, which of the following reagents will carry out the reaction shown below? So we have an acid chloride and we wish to convert it to an ester. So let's look at each of our choices. A is a Grignard reagent. if you add a Grignard reagent to an acid chloride, it's going to add two R groups and convert the acid chloride into an alcohol. Since we don't have an alcohol, A is out. Now, B is called the Gilman reagent or the lithium dialkyl cuprate reagent. And if you put that with an acid chloride, it's going to add one R group and convert the acid chloride into a ketone, which is not an ester. So answer choice B is not the correct one. C is an alcohol. An alcohol plus an acid chloride will make an ester, so C is the right answer. And D is an ester. If you put an ester with an acid chloride, I've never seen it make another ester, so we're going to eliminate answer choice D. Now, if you understand how these reactions work already, feel free to fast forward to question 7. But if you want to see the mechanism, feel free to continue watching. So let's start with the Grignard reagent. The carbon that's attached to the magnesium is partially negative, and it's attracted to this partially positive carbon. And so we're going to create a new carbon-carbon bond. As it attacks the carbonyl-carbon, the pi bond breaks. And we're going to have this a tetrahedral intermediate. So what we need to do is add the ethyl group to this carbon. Now the magnesium, which has a plus charge, it forms an ionic bond with the negatively charged oxygen. So what's going to happen now is this tetrahedral intermediate is going to collapse, and chlorine, the leaving group, will leave as chloride. And so right now we have a ketone. But the Grignard reaction does not stop there. The Grignard reagent will react with the ketone as well. So another Grignard molecule will attack the carbonyl-carbon, and then the pi bond's going to break. So this time, there are no leaving groups. So this is going to be our answer, because I really didn't add step 2. But step 2, usually you would add H3O+. Once you add H3O+, then it converts into an alcohol. So it's going to look like this, a tertiary alcohol. This oxygen is going to grab a proton from H3O+. So now for the second reaction, that is between the acid chloride and the Gilman reagent. So we have a copper atom attached to two ethyl groups. And copper has a negative formal charge because it's in the +1 oxidation state, and lithium has a plus charge. So only one of the R groups is nucleophilic. And so this R group attacks the carbonyl-carbon. And this part is going to be very similar to the first step of the mechanism of the Grignard reagent with the acid chloride. So we're going to get a tetrahedral intermediate. And we're just going to add only one R group. So right now the lithium ion is with the oxygen with the negative charge. The copper now has only one R group, and so it looks like this. And so it's not going to react anymore, so we're not going to worry about it. So this oxygen is going to reform a double bond and expel the leaving group. So if you choose to use the Gilman reagent, it stops at the ketone level. So it's very good for converting esters and acid chlorides into ketones. By the way, if you put the ester with the Gilman reagent, the mechanism is exactly the same. The only difference is instead of a chlorine, you'll have like a methoxy group, an OCH3. Okay, so now let's consider the mechanism with the acid chloride and the alcohol. So the alcohol will attack the carbon-O-carbon. And just like before, we're going to get a tetrahedral intermediate. But this time, instead of having an ethyl group, we have an ethoxy group, an OCH2CH3 group. Because answer choice B is very close to answer choice C. The only difference is it differs by an oxygen. And just like before, the leaving group is going to leave. So as you can see, the mechanism is very similar. And now we have our desired product, which is an ester. And so that's the mechanism for the conversion of an acid chloride into an ester. Number 7, complete the reaction sequence. So we have cyclohexanol reacting with PCC, and then we have some other reagents as well. So what does PCC do to an alcohol? If it's a primary alcohol, PCC can oxidize it to an aldehyde, and it can oxidize secondary alcohols into a ketone. So that's the end result of the first part. Now, what happens if we take cyclohexanone and react it with triphenylphosphine, and alkyl halide, and butyllithium? What do you think the major product will be? If you recognize these reagents, you'll know that it's part of the Wittig reaction, or some people say the Wittig reaction. The Wittig reaction, or Wittig reaction, it converts ketones into alkenes. So knowing that fact, you can eliminate answer choice A and answer choice B. So we're down between C and D. Now, if you want to quickly get the answer, notice the carbon that has the iodine atom. That is the carbon that is going to connect to this carbon. So it's the secondary carbon. Notice how we have, relative to that carbon, we have an ethyl on the right and a methyl on the left. D is going to be the answer. We have a methyl on one side and an ethyl group on another side. Let me show you the mechanism for this reaction. So the first thing that happens, triphenylphosphine reacts with 2-iodobutane. The phosphorus atom is a very good nucleophile, and so it attacks the carbon from the back, expelling the iodine group. So now we have a phosphorus attached to a carbon that has a methyl on one side and an ethyl on the other side. But I'm going to redraw it like this. This carbon has a methyl group, a hydrogen, and an ethyl group. Whenever a phosphorus atom has 4 bonds, it has a plus charge. Now we also have butyllithium as well. Butyllithium is a very powerful base. And butyllithium is used to remove the hydrogen atom on the carbon that's attached to the phosphorus group. And then this bond is going to break. It's going to put a lone pair on the carbon atom. So now we have our ylide, which looks like this. and it has a negative charge now. Now the ylide is stabilized by resonance. But I'm going to use this form for the mechanism. So once we pair up cyclohexanone with the ylide, the carbon with the negative charge is attracted to the carbonyl-carbon because it has a partial positive charge. So whenever you have a nucleophilic carbon and an electrophilic carbon, those two will connect and form a carbon-carbon bond. And then this bond is going to break. That's going to open up. So now we have this intermediate. And then what's going to happen next is this negatively charged oxygen atom is going to attack the positively charged phosphorus group to form a four-membered ring known as a beta-ene group or betaine group. So whenever a bond breaks, let's say a bond between carbon and bromine, because bromine is more electronegative than carbon, when the bond breaks, the electrons will go towards the more electronegative atom. So you would get a carbocation and a bromide ion. Conversely, let's say if you have a carbon-hydrogen bond, carbon is more electronegative than hydrogen. So when that bond breaks, you get a carbanion. So understanding that is going to help us to see how we can write the mechanisms for the next step. Oxygen is more electronegative than phosphorus. So oxygen bears a negative charge, phosphorus bears the positive charge. This carbon atom is partially positive with respect to the oxygen atom. And the carbon that's attached to phosphorus, this carbon is partially negative because carbon is more electronegative than phosphorus. Carbon is closer to fluorine than phosphorus is. So when the carbon-oxygen bond breaks, those electrons will go towards the more electronegative phosphorus atom. The more electronegative oxygen atom. And when the carbon-phosphorus bond breaks, those electrons will go towards the more electronegative carbon atom. So as you can see, the atom that's more electronegative pulls the electrons toward itself when the bond breaks. So the product of this reaction, we get triphenylphosphine oxide, and we get a carbon-carbon double bond. So as you can see, this is the end product for this reaction. So whenever you have a ketone, and if you're using the Wittig or the Wittig reaction, you're going to get an alkene as your end product. So that's what you want to take from this. And make sure you attach the carbonyl-carbon to the carbon that had the leaving group, the iodine. So just for the sake of practice, let's say if we have this ketone, and let's say the reagents are triphenylphosphine 3-iodohexane and butyllithium. If you quickly want to draw the major product, get rid of the oxygen, write the double bond, and connect it to the carbon that has the iodine. So notice that on the left side of that carbon you have an ethyl group, and on the right side you have a propyl group. So that's what you want to draw here. You want to draw the ethyl group and the propyl group, and that is going to be the answer, the alkene that forms as a product of the Wittig reaction. Number 8. Which of the following diene and dienophile will produce the product shown below? So this is the Diels-Alder reaction, and the diene is the one that has 2 double bonds, and the dienophile is the electrophile that has just 1 double bond. So this is the dienophile. So which answer choices can we eliminate? Well, let's count the carbon atoms. We have 1, 2, 3, 4, 5, 6, 7 carbon atoms, not including the 2 nitro groups. So we can eliminate choice C because there are 6 carbon atoms. So choice C is eliminated. And we could eliminate choice D as well. Choice D has a total of 8 carbons, not 7, if you don't count the nitro groups. So D is out. Now, if you count the carbons for answer choice A and B, they're both 7, so we need to look at something else. The fact that we have a bicyclic compound as a product means that we need to start with a ring. The Diels-Alder reaction creates a ring, but if we start with a ring, we'll have a total of 2 rings. And so, knowing that, this will tell you that choice B is the correct answer. Let's go over the mechanism real quick for answer choice A and B. So for choice A, here's what's going to happen. Let's say that this is carbon 1, 2, 3, 4, and this is 5 and 6. The Diels-Alder reaction, it makes 6 carbon rings, or I mean to say 6 membered rings. So this double bond is going to, the pi electrons in the double bond is going to connect carbon 1 and 6, and this double bond will move here, and the double bond between carbons 3 and 4, the pi electrons will be used to connect 4 and 5. But let me use a different color so you can see the connections. So here are the pi electrons in the double bond between carbons 5 and 6, and here are the pi electrons in the double bond between carbons 3 and 4. So there's also a double bond between carbons 2 and 3, and we still have a methyl group. And notice that the nitro groups are trans with respect to each other, so they're going to remain that way. So as you can see, if the diene doesn't start as a ring, you don't get a bicyclic compound. You simply get just a regular monocyclic compound, just 1 ring. But if the diene was in the ring already, we would get a bicyclic compound. This will be carbon 1, 2, 3, 4, 5, and 6. And let's call this other carbon, carbon A. So here's a 6-membered ring drawn differently. So this is carbon 1, 2, 3, and 4. So there's going to be a double bond between 2 and 3, just like we had it here. And on 5 and 6, we have the 2 nitro groups, but because they're trans with respect to each other, one is going to be in the exo position, the other is going to be in the endo position. Now, this carbon, carbon A, is on top. It's over here. So when you start with a ring, you're going to get two rings, a bicyclic compound. If you don't start with a ring, you'll just get a one-ring system. You won't get a bicyclic compound. So those are just some basics of the Diels-Alder reaction, so make sure you review that. And that's it for this question. Number 9. What is the product of the reaction shown below? So we have a diketone, sodium hydroxide, heat, and looking at our answer choices, we see that we're going to form a 6-membered ring. This reaction is the intramolecular aldol reaction. Sodium hydroxide will be used to remove an alpha hydrogen. But there's some answer choices that we can eliminate. If you know it's an aldol reaction, there are two types of products. The first product is a beta hydroxy aldehyde or ketone. What this means is that the OH group should be on the beta carbon. So if we look at answer choice A, relative to the ketone, the first carbon away from it is the alpha carbon, and this is a beta carbon. So that's a beta hydroxy ketone. But if you look at B, this is the alpha carbon, that's the beta carbon, this is the gamma carbon. The hydroxy group shouldn't be there, so we can eliminate B. Now the second product that you can get, if you add heat leads to dehydration, loss of water. So you're going to lose a hydrogen and an OH group, and you're going to form a double bond between the two. So dehydration will remove the alpha hydrogen and the OH, and it's going to put a double bond right in the middle. So that double bond should be between the alpha and beta carbon. So for answer choice D, the double bond is between the beta and the gamma carbon. Notice that it's not conjugated with this carbonyl group. Whenever you form a double bond by means of the aldol reaction, it should always be conjugated with the ketone or the aldehyde. So answer choice D is out. Looking at A and C, A would be the product if we didn't add heat. But because we heated the reaction, it's going to facilitate dehydration, so C is the correct answer. But now let's actually write up a mechanism to see how it works. So, under basic conditions, the first step is deprotonation. We need to remove the alpha hydrogen. And we're going to get a carbanion. Now, this negatively charged carbanion is going to attack the other carbonyl carbon. So this is going to be carbon 1, 2, 3, 4, 5, 6. So we're going to get a 6-membered ring. So carbon 2 has a ketone, so I'm going to make this carbon 2. This is going to be carbon 1, 3, 4, 5, and 6. Carbon 6 has a single bonded oxygen atom, and instead of having 2 lone pairs, it now has 3 and a negative charge. And there's a methyl group on carbon 6 as well. So notice that hydroxide, when it grabbed the hydrogen, it turned into water. So we're going to regenerate our hydroxide catalyst when this alkoxide ion grabs the hydrogen from water. So at this point, what we have is known as the aldol addition product. We have an alcohol and a ketone. Sometimes instead of a ketone, it could be an aldehyde. So if this reaction wasn't heated, this would be the product. But since it's heated, we need to take it to the next step or to the next level. So we still have an alpha hydrogen next to that ketone, and in the presence of heat, the hydroxide ion will remove this hydrogen via the E1CB reaction mechanism. So we're going to get the enolate ion initially. And we're going to use that enolate ion to get rid of the OH group. And so now we have our final answer. This is the alpha beta unsaturated ketone. So that's the answer of the intramolecular aldol reaction after dehydration. Number 10. Which of the following reagents will produce the product shown below with the greatest yield? So, looking at the product and comparing it to the reactant, we can see that we've added a methyl group to the left side. Or basically, we replaced an alpha hydrogen with a methyl group. And looking at our answer choices, we see that step 2 is the same, methyl bromide. The difference is in step 1. Should we use LDA as a base or NaH? NaH is sodium hydride. It's a small base, and LDA is a bulky base, lithium diisopropylamide. And the second thing we need to consider is the temperature. Should we use a very low temperature, negative 80 degrees Celsius, or a very high temperature? Now, to get the right answer, we need to realize that there are two products that compete against each other: the kinetic product and the thermodynamic product. And there are two alpha hydrogens that lead to those products: the blue hydrogen and the green hydrogen. Now, if we remove the blue hydrogen, we're going to get the kinetic enolate ion, which looks like this. And if we remove the green hydrogen, we're going to get the thermodynamic enolate ion, which looks like that. Now, you also need to know that if you use sodium hydride, it favors the formation of the thermodynamic product. Sodium hydride is a small base, and because the hydride ion is small, it can grab both the blue or the green hydrogen. So it prefers to grab the green hydrogen because it leads to the more stable thermodynamic product. If you look at the double bond, it's next to the methyl group, and that means that double bond is more substituted than the blue double bond. The more substituted a double bond is, or the more R groups it has, the more stable that particular alkene is, or that double bond. Because I guess this is really not an alkene, it's an enolate ion. Now, LDA is a bulky base, and because it's so huge, it's not going to go for the green hydrogen, even though it leads to the more stable enolate ion. Rather, the bulky base is going to go for the hydrogen that's more accessible, which is the blue hydrogen. This methyl group blocks the LDA from grabbing the green hydrogen, so it's going to go for the more accessible blue hydrogen. Now, the second thing is the temperature. A low temperature favors the kinetic product, and high temperature favors the thermodynamic product. So knowing that, looking at our answer, do we have the kinetic product or the thermodynamic product? Because the methyl group that we added was on the left side, that means that it's the kinetic product because it came from this double bond here, which is on the left side. The thermodynamic product, if we had that, we would have another methyl group on this side. But since we don't have it, it's the kinetic one. So we need to choose LDA, so we can eliminate answer choice C and answer choice B. And we need to choose a low temperature to get the best yield. So therefore, answer choice A is the correct answer. So now, let's write up a mechanism for this process. So the methyl group that was already existing on this cyclohexanone ring, I'm going to put it to the left side. I'm going to flip it to the left before it was on the right. It just makes it easier to show the mechanism. So LDA, it's a nitrogen atom with two isopropyl groups, and the nitrogen atom has two lone pairs, so it has a negative charge, and it's paired up with a lithium ion. So this bulky base is going to grab a hydrogen and create the enolate ion. So that's the first step, deprotonation. Now once we have the enolate ion, the second step is pretty straightforward. We just need to add the methyl bromide. So the oxygen with a negative charge is going to reform a double bond. It's going to use a lone pair to do that. And it's going to cause this double bond to become nucleophilic, forcing it to attack the methyl group, expelling the bromide leaving group. And so therefore, our answer looks like this. So here we get the kinetic product rather than the thermodynamic product. Number 11, complete this sequence. So for this problem, we need to find out which ring is more activated. The ring on the left, it sees this partially positive carbonyl group, and the carbonyl group is a meta-directin deactivator. It can pull electron density toward itself, thus deactivating the ring, making it more electrophilic or partially positive. Now, the ring on the right is activated. It sees this partially negative oxygen atom, which can donate electron density to the ring by means of the resonance effect, putting a partially negative charge on that ring. So the ring on the right is more reactive than the ring on the left. So therefore, any answer choice that has groups or substituents on the left ring is eliminated. We can eliminate answer choice A and C. So now we're down between B and D. So the first thing that happens, once we add this acid chloride to the ring, we're going to get this group, a ketone, just on the right side. And then once we add hydrazine, which is H2N NH2, that's the Wolff-Kishner reaction, it's going to reduce the ketone into a propyl group. So as we can see, both answers contain the propyl group, and this oxygen is an ortho-para director, so the propyl group went to the para position relative to the oxygen. Now the only difference is where the bromine is going to go. So will the bromine go ortho or meta with respect to the oxygen? Now keep in mind, even though this position is ortho with respect to the oxygen, the green arrow, the red arrow is ortho with respect to the propyl group. And both the oxygen and the propyl group are ortho-para directors. So in a situation like this, you got to find out who's going to win. So which group is more activating? Is it the oxygen or the alkyl group, the propyl group? It turns out oxygen is a much stronger electron donating group. The propyl group is a weak activating group, so the oxygen is going to win. So therefore, the oxygen is going to tell the bromine to go ortho with respect to itself. So B is the answer. But now let's write out everything. So the first reaction is a Friedel-Crafts acylation reaction. The catalyst takes away the chlorine group, and the carbonyl group adds itself to the ring. And it goes on the para position initially. And then in the next step, once we use hydrazine with potassium hydroxide, this is going to reduce the ketone into an alkane. Pretty much it gets rid of the carbonyl oxygen and it replaces it with 2 hydrogen atoms. But we don't have to show the hydrogen atoms, so we can simply write it as a propyl group. So once we get to this part, oxygen will direct the bromine ortho with respect to each other, with respect to itself, I should say. And the propyl group wants the bromine to go on the ortho position with respect to itself. But because oxygen is a more electron donating group, it's a more powerful activator relative to the propyl group. The bromine is going to go in this position. And so that's why we get that answer. Number 12. Which of the following compounds will show two signals in an H&MR spectrum? So we got to find out how many different types of hydrogens are in each of these compounds. So let's start with compound 1. We have a methyl group on top, so that would show as one signal. These two hydrogen atoms are identical to each other, so they would show as a second signal. We'll call it signal B. And there's another two hydrogens here, which are identical to each other. They're equidistant from the methyl group. They're 2 carbons away from it, so they have the exact same chemical or electronic environment. So we'll call it proton C. And then there's another proton here, which we'll call it, which would be the 4th signal. So compound 1 would show 4 signals in an H&MR spectrum. So we want a compound that shows 2 signals. So anything with compound 1 as an answer can be eliminated. So we're down between B and D. Looking at compound 2, the methyl groups are identical to each other. So we'll call it proton A. As we can see, there is symmetry across this line. So therefore, these two are identical to each other. And there's also symmetry here. So we can call this proton B as well. So all 4 of those protons are identical to each other. They have the exact same chemical environment. If you compare these two protons, they're both 1 carbon away from the methyl group. So compound 2 would show up as 2 signals. Compound 3 also has symmetry. These 3 methyl groups are identical to each other. Each methyl group is 2 carbons away from another methyl group. And the hydrogen atoms are all equidistant from each other, so they're all identical. So we'll call it signal B. So this will generate 2 signals as well. Now keep in mind, there are no hydrogen atoms on these carbons that I've indicated in green because those carbons have 4 bonds. So we can see compound 2 and 3 generated 2 signals, so chances are that's the answer. But for the sake of practice, let's see if we can find out how many signals are in compound 4. The 3 methyl groups in the tert-butyl group are identical because they're attached to the same carbon atom. And there's symmetry in the middle. So those 2 protons are identical to each other, and these 2 as well. We have at least 1 hydrogen on this isopropyl group, so we'll call it signal D. And then the 2 methyls, which are attached to that CH carbon, are identical to each other. So compound 4 shows up as 5 signals in a graph. So the correct answer is D. Compounds 2 and 3 shows 2 signals in an H&MR spectrum. So number 13, what is the major product? So here we have a ketone, cyclohexanone, and this amide, I believe it's a semi-carbazone group. But what do you think the major product for this reaction is? Do you think it's A, B, C, or D? Well, just to review, if you have a ketone and you add a primary amine, where it has an NH2 group, you're going to get the imine, which is a carbon double bonded to a nitrogen. And if you add, let's say, like a secondary amine where that nitrogen only has 1 hydrogen instead of 2 hydrogens, you get the enamine or anamine group, where you have a carbon single bonded to a nitrogen, but adjacent to a carbon double bond, like a C double bond C. So the enamine is basically an amine with an alkene. So if you look at answer choice B and D, those are an enamine. You could see the amine group next to an alkene. And answer choice A and C represents an imine functional group. So what we really need to decide is which nitrogen is most nucleophilic, which nitrogen will attack the carbonyl carbon, because each of these nitrogen atoms have lone pairs, but one of them is more nucleophilic than the other. So would you say we'll call this nitrogen A, nitrogen B, or nitrogen C? Nitrogen A and B are not amine nitrogens, they're amides. A nitrogen that's in an amide functional group are not nucleophilic, but the amine nitrogen is. Looking at nitrogen A, its lone pairs aren't available for a nucleophilic attack. As you can see, those lone pairs are busy resonating with the carbonyl oxygen. So nitrogen A is not very reactive. Nitrogen B is not reactive either. It can delocalize into the carbonyl group. So the nitrogen that's part of an amide functional group will not attack the carbonyl carbon. Nitrogen C doesn't delocalize into the carbonyl group. It's too far away. So this is the amine group that's going to react with the carbonyl group. And because it's an NH2, where meaning it's a primary amine, we should get the imine and not the enamine. So we can eliminate answer choice B and D. Now that we know we're supposed to get a carbon double bonded to a nitrogen atom, we need to distinguish between A and C. If we look at answer choice C, we can see that the amide nitrogen attacked the carbonyl group, which shouldn't be the case because that lone pair delocalizes into the carbonyl group. So answer choice C is out. Answer choice A is the correct one because this is the nitrogen that's 2 carbons away from the carbonyl group. That's the amine nitrogen, and that's the one that's going to attack the carbonyl compound. So let's review some reactions between amines and ketones. So let's say if you have a ketone and you add a primary amine to it, what you need to do is get rid of water. Water is going to be removed. And so replace the oxygen atom with the nitrogen atom. And then the nitrogen lost 2 hydrogens, so it only have the methyl group at this point. So that's the imine or amine functional group. You need a primary amine to get the amine. By the way, the amine group works under mildly acidic conditions, meaning the pH has to be around 4 to 5 to get the greatest yield. If it's not at that range, your yield for the amine will be low. Now let's say if we react a ketone with a secondary amine. Let's use this one because it's very common, especially in the Stork-enamine reaction. Now what's going to happen is you're going to get the enamine or the enamine, which is an alkene plus an amine. So you're still going to lose water, but you're going to lose this oxygen, this hydrogen, and one of the alpha hydrogens, and that's going to create water. So this time, instead of having a carbon double bonded to a nitrogen, it's going to be a single bond. And then you're going to have your nitrogen with its 2 R groups. It's a lone pair, but the double bond is going to be between the carbonyl group and the alpha hydrogen, so it's going to be here. So you get the enamine. By the way, let's say if we have cyclohexanone and there's a methyl group, and let's say you wish to add this same secondary amine. So we know we're going to get the enamine as a product, but there's 2 possible locations in which the double bond can go. It can go on the right side, or it can go on the left side. So which of these 2 products is favored? if you have to choose, pick the one that generates the most stable alkene. The most stable alkene is the one that's closer to the R group, the methyl group. So this form is more favored. It's more stable. Here we have this alkene has 3 R groups, so it's tri-substituted, and this alkene has 2 R groups, so it's di-substituted, not counting the nitrogen atom. Number 14, which compound is not aromatic? Now, just to review, for a compound to be aromatic, it needs to have 6 pi electrons based on Huckel's number, or Huckel's rule, 4n plus 2, and it needs to be cyclic, completely conjugated around the entire ring. All of the atoms must be sp2 hybridized, so the whole structure has to be flat or planar. So let's look at each one. Let's start with compound A, known as pyrrole. And every double bond represents 2 pi electrons, so this is going to be 2, 4, and the lone pair is 6. Now if you look at B, it's 2, 4, also 6 pi electrons, but we don't count this lone pair. Now, if you're wondering when you should know if you should count the lone pair or not, here's a review. So let's say if you have some generic atom A. Only count the lone pair if it makes the 4th group. So let's say if this is number 1, group number 2, and then this is number 3, don't count it, because the lone pair make the 3rd group. But let's say if you have this scenario where this is group 1, group 2, group 3, and then group 4, count the lone pair as towards pi electrons. Or let's say if you have this situation, group 1, group 2, group 3, don't count it, group 4, count the lone pair. So if the lone pair makes the 4th group, count it. That's a quick and simple way to tell if the lone pair is going to be counted. So this lone pair is not counted, so we still have 6 pi electrons. And if you look at A and B, all of the carbon atoms are sp2 hybridized, and it's completely conjugated. So A and B are both aromatic. Looking at compound C, we have 2, 4, 6 pi electrons. Not 8, because we don't count both lone pairs. It's pretty much this situation. We count one of the 2 lone pairs. So answer choice C is also aromatic. Now D may appear to be aromatic. It has 2, 4. We do count this lone pair, 6. We have this situation. We have a carbon atom that's attached to 2 other carbon atoms. There's an invisible hydrogen that you don't see, and a lone pair. So the lone pair makes the 4th group, so we count it towards pi electrons. So even though this compound has 6 pi electrons, notice that this carbon, which I indicated in red, it's an sp3 hybridized carbon. It has 2 hydrogens. And because it's an sp3 hybrid carbon, this lone pair cannot move in this direction. That lone pair can only resonate around these 5 carbon atoms. It can't fully resonate around the entire 6 carbon cyclic structure. So this sp3 carbon pretty much doesn't allow conjugation around the entire ring. Plus, it's an sp3 carbon is not planar. So if it's not planar, it's not going to be aromatic. So D is the answer. D is a non-aromatic compound. A, B, and C are aromatic. Number 15. Which compound is consistent with the H-NMR spectrum shown below? So if we look at the functional groups present, we can see that we have an aldehyde, an ester, an ether, and a benzene ring. The first thing that we could distinguish is the aldehyde. So we're focused on the hydrogens though. The aldehyde hydrogen has a signal around 9 to 10. And the fact that we don't see that on the graph means that we can eliminate answer choice A. Now, the next thing that we can focus on is the signals around 6.5 to 8.5. If you see signals in this region, that is the hydrogens on the benzene ring. So the fact that we have those signals means that there should be a benzene ring, so we can eliminate answer choice B. Now, for the other signals that are less than 4, there's some things that you need to know. If you have a regular CH3 next to, let's say, a CH2, a regular, so basically an alkane CH3 with nothing special around it, the signal is going to be around 1. Now, let's say if you have a carbon next to a special group, like an electronegative atom, we'll call it X. It can be an oxygen, it can be a nitrogen, it can be a chlorine or a bromine. Usually that signal is around 3 to 4. And let's say if you have, let's see where I can put this one, a CH3 next to a carbonyl group, that signal is around 2 to 2.5, so we'll say like 2.3. And also, if you have, let's say, a CH3 next to a benzene ring, that signal will also be around 2.3. So now let's analyze C and D. Let's start with compound D. Here we have a CH3 next to a carbonyl group, so that's going to be around 2.3. And here we have a CH2 next to an oxygen, so we're going to say 3.5. It's supposed to be between 3 to 4. And here we have a CH3, so we'll say that's around 1. The CH3 is next to the CH2. So we have those signals in the graph. So now let's look at answer choice C. Here we have a CH3 as well. That's 2.3. Actually, no, this CH3 is not 2.3. This CH3 is actually next to an oxygen, not to a carbonyl group. It's a small little difference, but it's very important. So because that CH3 is next to an oxygen, we have this signal, 3.5. Here we have a CH2 next to an oxygen, so that's 3.5. And a CH3 next to a CH2, and that's around 1. So answer choice C, we should have 2 signals around 3.5, not 1. So we could eliminate answer choice C, which means the correct answer is D. Now, just to review, we can also look at the spin splitting pattern. This CH3 doesn't have any adjacent carbons that have hydrogen, so it's a singlet. And as we can see, we do have a singlet around 2. Looking at the CH2, it's adjacent to a carbon that has 3 hydrogens, so using the n+1 rule, it should have a splitting pattern of 4, so it should appear as a quartet. And this, we do see the quartet here. It splits in 4, the signal splits into 4 smaller peaks. And the CH3 is adjacent to a CH2, so 2 plus 1 is 3, so that's a triplet. And we do see the triplet around 1. So compound D is the correct answer.